For nearly a century, cosmology has described a universe born in fire, expanding through space and time, dominated by unseen components. The lambda CDM model has been extraordinarily successful, but every model rests on assumptions. What if cosmic redshift has another origin? What if time itself is not what we think it is? This is the Exochronous universe, rethinking cosmology from first principles. Last time we reached one of the great unsolved questions in cosmology. Somehow the early universe was left with just a tiny excess of matter over antimatter. Almost everything else annihilated into radiation. Without that minute imbalance, there would be no stars, no planets, and no observers to wonder how any of this happened. But surviving matter was only the beginning of the story. Those surviving particles still had to assemble themselves into the first atomic nuclei. Remarkably, that process is understood far better than baryogenesis itself. It combines laboratory nuclear physics, astronomical observations, and numerical modelling to make quantitative predictions that can be tested directly against the universe we observe today. Primordial nucleosynthesis has therefore become one of the strongest empirical foundations of modern cosmology. We are now only a few seconds after the beginning of the hot Big Bang. Temperatures exceed several billion degrees. The universe contains no atoms, no molecules, no stars. Only an extremely hot plasma of elementary particles. Protons and neutrons constantly collide with one another. Electrons remain unbound. Photons carry enormous energies. Every particle interacts continuously with every other. The universe is cooling rapidly, and that changing temperature controls everything that follows. At these enormous temperatures, protons and neutrons continually transform into one another through the weak nuclear interaction. The two particle types remain in thermal equilibrium. As the temperature falls, however, these reactions become progressively less frequent. Eventually, they can no longer keep pace with the changing conditions. Physicists describe this as freeze-out. The proton-to-neutron ratio effectively becomes fixed. From this point onward, another process takes over. Free neutrons are unstable. Each survives on average for about 15 minutes before undergoing beta decay. Some transform into protons, emitting an electron and an antineutrino. As the minutes pass, the neutron population steadily declines. By the time nuclear fusion begins, only about 1 neutron remains for every 7 protons. That simple ratio will determine how much helium the universe can ultimately produce. One might expect nuclear fusion to begin immediately. After all, protons and neutrons are already colliding constantly. But something prevents it. Whenever a proton and neutron combine to form a deuterium nucleus, energetic photons almost instantly break it apart again. The radiation field is simply too energetic. The first step towards building heavier nuclei cannot survive. The universe has reached an unexpected bottleneck. Only after further cooling does the balance begin to change. More and more deuterium nuclei survive each second than are destroyed. That small change unlocks every reaction that follows. Once stable deuterium becomes abundant, nuclear fusion accelerates dramatically. Deuterium nuclei collide with protons to form helium-3. Some reactions briefly produce tritium. Further collisions rapidly assemble helium-4. Helium-4 is exceptionally stable. Its nucleus contains 2 protons and 2 neutrons bound together with remarkable efficiency. As soon as enough building blocks exist, the universe quickly locks most surviving neutrons into helium nuclei. Small quantities of lithium also form through more complex reaction chains. But these reactions are comparatively rare. Within only a few minutes, nearly all primordial nuclear fusion is complete. The chemical composition of the universe has largely been established. Fusion does not continue indefinitely. As the universe cools further, energetic collisions become increasingly rare. There is another obstacle. Nature provides no stable nuclei containing either 5 or 8 nucleons. Those missing stepping stones make it extraordinarily difficult to build heavier elements under these conditions. Primordial nucleosynthesis therefore comes to an end after only a few minutes. The universe is left composed almost entirely of hydrogen and helium, with only tiny traces of lithium. Everything else must wait for the first stars. The remarkable feature of primordial nucleosynthesis is not simply that it explains how the first nuclei formed. It makes quantitative predictions. The relevant nuclear reaction rates have been measured experimentally in laboratories. Those measurements are combined with thermodynamics, particle physics, and the cosmological model describing the conditions of the early universe. Computer simulations then calculate the abundances of each light element. These predictions can be compared directly with astronomical observations. The agreement is striking. Hydrogen, helium, and deuterium all match the predicted abundances remarkably well. Lithium remains more problematic. Observations consistently find less primordial lithium than the simplest calculations predict. Known as the lithium problem, this discrepancy remains an active area of research. It may point towards subtle astrophysical processes, uncertainties in nuclear physics, or perhaps new physics that has yet to be discovered. Science has not yet reached a final answer. Within the first few minutes, the universe completed its first, and in many ways its most important, act of chemistry. The result was remarkably simple. Around 3/4 hydrogen by mass, 1/4 helium, and only tiny traces of heavier light elements such as deuterium, helium-3, and lithium. These primordial abundances have remained largely unchanged ever since. They provide one of the earliest observable relics of the hot, dense universe, and any successful cosmological model must explain why they have precisely the values we measure today. But although nucleosynthesis is now complete, the story of the early universe is only beginning. The matter created during these first few minutes was not distributed perfectly smoothly. Tiny variations in density would continue to evolve under the influence of gravity, while pressure waves travelling through the primordial plasma left subtle patterns imprinted across the cosmos. Those ancient patterns can still be detected today on the largest scales of the universe. In the next episode, we'll explore how these primordial sound waves became the baryon acoustic oscillations, one of the most powerful observational tools in modern cosmology, and another key test that every cosmological model must successfully explain.